Okay, let me give you some corrections of the lectures I gave last time. Correction from last lecture. Okay, so G, this is a Lie algebra, and X is an element in G. Then we can define adjoint map from G to G given by add X of Y equals X comma Y. Okay. And because once X is given, we obtain a map from G to G. So add X is in what? Endomorphism of G. Okay? So it's a linear map from G to G. So it's an endomorphism. And we can give a Lie bracket structure here. This is we know how to give the Lie bracket structure here. This is FG minus G8 F. So last time I wrote so add is what? Once X is given, we get an endomorphism of G. So it's a map from G, Lie algebra G to endomorphism of G, which is also a Lie algebra. So this is a map from Lie algebra to Lie algebra. So it turns out that this is a Lie algebra homomorphism. And I think I wrote something like this. Add X, because add X okay, I'm just writing the thing that I wrote last time. And this is just Jacobi identity, and this is add X is a derivation. All right, so yeah, it's true that if you rewrite this using this definition, then this is equivalent to the Jacobi identity. So this is good, okay? This is okay. And this really means, what this really is saying is that this map is a derivation. This is the definition of the derivation. So this is okay, but this one is a little questionable. So instead of this, the better way of writing this equivalent or this, so let's just look at the definition. What's the definition of Lie algebra homomorphism? This means AD of X comma Y. This is by definition. This equals ADX ADY, right? But you know, ADX is just, we will write this in this way. This is how we write adjoint map. So this is really the same as add X comma Y equals, but now this bracket is in endomorphism of G, so the Lie bracket is given by this commutator. So it's ADX ADY minus ADY ADX. So this is the same as this, which is of course the same as this, but this follows from this is really a Jacobi identity. That's another way of considering the Jacobi identity. Once we have Z here, Z, then this eventually becomes Jacobi identity. So this is what I want to say. So instead of this, just use this relation. Okay. Oh, and by the way, this one is a Lie algebra homomorphism. What about this? This is also a linear map from Lie algebra to itself. So you might be wondering whether this is a Lie algebra homomorphism. Actually, if you remember, I was trying to write this as a Lie algebra Lie algebra homomorphism, but this is not Lie algebra isomorphism. Lie algebra homomorphism in general. So try to find a counterexample. You can find the counterexample. So this one is not. This is a Lie algebra homomorphism. Okay. Then let's continue from the last lecture then. So last time we defined this. So G, the matrix Lie group in GL, say, and C. Then the Lie algebra of G is denoted like this Gothic G, which is the set of all matrices. E to the tx is in G for all t real. So you collect all matrices X such that E to the tx is there. So this is it's important that T, we only consider real T. So whenever we have a matrix Lie group G, we have a Lie algebra, corresponding Lie algebra. Okay. So in this definition, this is just a set, but it turns out that this is a Lie algebra, real Lie algebra. So G is a real Lie algebra. Where the bracket is defined like the usual way for the matrices with this bracket. It's not necessarily a complex Lie algebra, but sometimes it could be, but not always. So this is what we did last time. And G, a matrix Lie group, G is called complex if the corresponding, if its Lie algebra G is a complex subspace of M and C. Complex subspace. So it means, this means complex subalgebra means if X is in G, then I times X must be in G. This is what I mean by this complex subspace. Just from the definition, this is not guaranteed that we have IET there. So if that's true, then the matrix Lie group is called complex. An example, these are complex SL and C, SP and C. These are complex matrix Lie groups. Okay. And so now we have this matrix Lie group and corresponding Lie algebra. So we want to see their connection, their relation. So if G is commutative, then its Lie algebra is also commutative. But the converse is not true. But converse is not always true in general. Shall we see a proof or not? Do you want to see the proof? Or do you just want to read the proof in the textbook? I think proof is quite interesting, so I'll just skip it. Read it. It's interesting, so it's not that difficult and interesting, so I'll just leave it to you. All right. Example. But here, converse, we will see partial converse of this, but converse is not true in general. So now we have these many examples of matrix Lie groups, like general linear group, special linear group, etc. So we will use this notation. So we use small lowercase letters to indicate the Lie algebra of the corresponding Lie group, Lie algebra of G, L, and C. And of course, we can write N, R in the obvious way. So we will just use, whenever we have some notation, like, so usually we use capital letters for this matrix Lie group, and then their corresponding Lie algebras will be written the same way, except we are now using lowercase alphabet. So of course SL is like special linear group. It should be R, right? And then etc. etc. Like SON, small lowercase, or U of N. These can also all define, like SPN, etc. Yeah, defined in the same way. Okay. All right. So we know what this is, right? So it's a general linear group means set of invertible matrices. A special linear group set of matrices of determinant 1. But what is, can you have a simple description for this? And the answer is yes. They also have nice and simple characterization of the elements. General linear algebra. This is the same as all matrices. So basically, it's the set of all matrices, all n by n matrices. And of course, if I replace this by R, it's still the same. And special linear group or linear algebra, C or R. This is now a set of matrices of trace 0. Here, of course, we use R. Let's prove one of these. Let's prove this thing. Okay. Suppose that if X and has trace 0, what happens? We want to know that it is in this set, right? But what is this? What is this? This is the Lie algebra of special linear group. So to check, we want to know this. We want to show that X is in S, L, and C. But what does this mean? What does this mean? But by definition of the Lie algebra, this means e to the tx is in S, L, and C. But this means what? Determinant is 1. So we want to know this. But is this true? But if you remember, we have a theorem like this. Determinant of this is what? E to the trace of x, tx. Okay? But trace, this t real number can be put outside. So trace 0, so yeah, that's true. So this is the proof, basically. Okay? So trace 0 is equivalent to saying that this is, determinant of this is 1 always. I think I have to say some more. All right. Let's go in one direction, because the other one, I think we need some more instead of, okay. Let's go one direction only for now. We want to show this, but it is there because of this. So one direction is done. So x is in S, L, and C. So we have just checked one direction. So now suppose x is in now S, L, and C. We want to show that the trace is 0. Okay? So by definition, e to the tx is 0. Oh, sorry. Determinant is 1 by definition. Now, what is the trace? Trace of x is the t, we can say e to the t trace of x, t equals 0. This is true. This is just, it's not even matrix exponent, just one variable exponent, right? But this is equal to the dt determinant of e to the tx, t equals 0. Okay? Because this is equal to this. But now what? This is always 1, so the derivative is going to be 0, so it's 0. So trace is 0. Okay? So they are the same. So for other Lie algebras, there are also simple descriptions like this. So other Lie algebras, like U of n, SU of n, etc., also have simple description. For example, U of n is a set of matrices, n by n complex matrices, such that this equals minus x. And so just read the textbook for the other examples. Okay. Now I'm going to move on to the next section. It's about Lie groups and Lie algebra homomorphism. So we have a Lie group or matrix Lie group. Then we have the corresponding matrix, corresponding Lie algebra. So what if we have Lie group homomorphism? Then one may ask, do we have some kind of corresponding Lie algebra homomorphism? And this theorem says yes. So these are matrix Lie groups, and G and H, these are corresponding Lie algebras. Okay, so G corresponding to G, H corresponding to H, of course. And suppose that we have a map, a Lie group homomorphism, Lie group homomorphism. Then there exists a unique, this means there exists, this means unique, R linear map, phi from G to H, such that phi of e to the x is equal to e to the phi of x for all x in G. So there is a unique R linear map with this property. And I'm going to write some more. So for right now, we don't know yet whether this phi is a Lie algebra homomorphism, but it turns out that it is so. So for now, we just know that there is a unique map, R linear map satisfying this. And this map satisfies, so first, phi of x, ax a inverse equals capital A x a inverse for all x in G, A in Lie group G. It doesn't matter, but we can have minus over there, but Lie group homomorphism, so it doesn't matter. And phi x comma y equals phi x phi y for all x y in G. So this means this is really a Lie algebra homomorphism. And third, this one is useful. Phi of x, this can be computed using the capital phi, d dt, capital phi of e to the tx, when t is set to be equal to 0 for all x in G. So by this point 2, we know that every Lie group, matrix Lie group homomorphism induces a unique Lie algebra homomorphism. So this second one says that this phi is a Lie algebra homomorphism by this. This point, this property will be used later to compute this one. All right. Okay, now I'm going to define a special map on G related to this Lie group, which is quite similar to what we have seen. So G, at least its name, matrix Lie group as before, and G is the Lie algebra of G. And let's say A is an element in the Lie group. Then we define the adjoint map. Adjoint map AD sub A, but notice that we are now using capital A here. This is a map from G to G, this Lie algebra. The adjoint map is given by AD A of x equals, it's just a conjugate by A, like that. This is the definition of the adjoint map. Yeah. But in fact, we have to check this whether this is really a map from G to G, because we don't know yet whether this is really in G. But that's not difficult, so let's check that. If X is in G, then what happens? Then e to the, by definition, Tx is in G for all T real, right? So we want to know that this is in G. So e to the T A, we see this. What is this? This is just A. You can move this anywhere. The T, let's say T is there. But we have seen that whenever we have a matrix exponent like this, we can kind of move this outside. So A, E, T, X, A inverse. Now, this is in G. This is in G. This is in G. So everything is in G. So yes, for all T, this is in G. That means this part is in this Lie algebra. So it is indeed a map from the Lie algebra to itself. All right. So this, I'm going to use this notation. This is the group of all linear maps from G to G. So for this definition, we don't need the structure of the Lie algebra. This only consider this as a vector space. So this is really like this, and see if it is complex. If like G dimension is n, right? So just forget about the Lie algebra structure and then just regard this as a vector space, and then this is the usual definition for general linear group. So it is a matrix Lie group because it is really the same as this. It's isomorphic to this, considering only the G as a vector space. Like we consider this as the set of linear maps from G to G. This is just like that. Okay. Now, if you remember, I told you that, so we want to now compare this with add X. We checked, we know this. So we have two adjoint maps. Like they're different, but they have the same name, like adjoint map written in capital letter, adjoint map written with this lowercase letter. This is x comma y, and this is defined like that. They're different. Their domains are different, etc. And this is not a Lie algebra homomorphism, but this one, let's see, G and G as before, meaning matrix Lie group is corresponding Lie algebra, and add is a map from G to GLG. Because once we have A here, this gets mapped to AD sub A. But this is an invertible matrix, invertible linear transformation, so it is in GLG. Okay? This is a Lie group homomorphism. Just like this small AD is a Lie algebra homomorphism. These are both Lie groups, and these are naturally is a Lie group homomorphism. Lie group homomorphism means it's a continuous map, which is pretty obvious, and this means continuous. And what? Group homomorphism, meaning AB equals ADA, ADB, which is very easy to check just by using the definition. Furthermore, for all A in G, AD sub A. So once A is fixed, this is a map. We know that this is a map from its Lie algebra to itself. This is a Lie algebra homomorphism, i.e. ADA, AD. So for this small AD, this was false, but it's true for this adjoint map. Okay, let's see a proof. The first one is easy, so it's check easy. So we will check this. This is also easy, by the way. Okay, let's look at the left-hand side. So I'm trying to prove this. Left-hand side is okay. Let me write. Just use the definition. This is A something A inverse. That's the definition of this. But what about this? XY minus YX. Okay, and what about the right-hand side? Here is add a x, add a y, minus add a y, add a x, but just use the definition, A inverse. Is A inverse and A, they cancel each other, so we get exactly what we wanted, which is, of course, okay, cancel this, so they are the same. All right. Okay, now let's go to the next page. So again, G is Lie algebra. Then we already defined GLG, capital GLG. This is the set of all invertible matrix linear maps F from G to G. Okay, there's a Lie group. And small GLG is by definition is all linear maps, not necessarily invertible. But now we're going to give a Lie bracket structure as usual. This is composition of maps. Okay. Then this is a Lie algebra. In fact, if we are it doesn't matter whether this is a Lie algebra or not. Actually, if this is just a vector space, these are defined. Just good enough. Okay, people doing that. Then, in fact, this is the Lie algebra of this Lie group. So GLG is the Lie algebra corresponding to this GLG. But this is in fact not new. We already have seen this because let's say suppose G is a real Lie algebra. It's a real vector space of dimension n, let's say. Then that this means, in other words, R to the n, something like that, vector space isomorphism. Then what is this? GLG is nothing but a general linear group of nr, or maybe like that. GL of G is general linear algebra, but we've already seen that this is the Lie algebra of this. So I'm just replaced this vector space by Lie algebra, but we are only using vector space structure there, so that's okay. All right. Okay, now it's time to look at the connection between the two adjoint maps. They are closely related, as you can expect from their names. Let's say phi is the adjoint map, this capital letter adjoint. And then we know that this is a Lie group homomorphism. We have already seen this as a theorem. We have two Lie groups, and we have a Lie group homomorphism, capital phi. Then we know that we have a corresponding Lie algebra homomorphism. So here, the corresponding Lie algebra homomorphism will be the Lie algebra of G, which is denoted by this G, and we know that this is GLG. Okay? So we have Lie algebra homomorphism, the unique homomorphism, like that. So now we are saying that this is ad. Then what is this? What is this then? It is AD. So that's the theorem. Okay. So proposition V is AD, using this notation. Okay. So, all right. Okay, let's put it a little more. If this is AD, then the corresponding Lie algebra homomorphism is AD. Okay. Make sense? In other words, Vx is ADX. So I'm just writing this in a or V of x. V of x is a map from G to G. So we can put another element in G. This is x comma y. I'm just writing the same thing, just in a different way, but they are basically the same. Okay, let's see a proof of this. We know that from the theorem before, phi of x, this is point 3 of the, okay, let me write it down, 3.28 in the textbook, point 3, the third item. This is equal, can be computed in this way, phi e to the tx, t equals 0. So this is a property that we have seen. So using this, we can actually compute this. So what is that? So because phi, capital Phi is the adjoint, and this is going to be adjoint sub e tx, t goes to 0. So we want to know whether this is true, because they are all the same thing. So let's compute that. Because this map is the limit, our derivative with t equals 0, d dt, just replace, so basically it's like putting y inside this function, okay? So, but what is add? It's like e to the tx and e to the minus tx, and y is inside like that, and then we want to put t equals 0, all right? But what is this? This, we can use a product rule here for even for these matrices. So we take the derivative of this is, we don't need dt, e to the tx, and then xy e to the minus tx, plus e to the tx, y e to the minus tx, and minus x, and then we set t equals 0 at the end. What's that? So if t equals 0, this is just 1, 1, 1, 1, 1, minus. So it's xy minus yx, which is exactly what we wanted. So yes, it is the adjoint map. Or equivalently, in other words, this or this, or equivalently, ad e to the x equals e to the adx. This is true. Okay, so also a proposition. Because we know that, no, let's go back to that. Just real quick. Because of this, I'm just rewriting this using the adjoint maps. It just follows from that. Okay. Okay, let's see an interesting consequence of this. So let me rewrite that. Ad e to the x equals e to the adx. All right? And let's consider this particular case, G, L, and C. So set of all n by n matrices or linear transformations. Then what is G? The G, L, and C, which is the set of all matrices in this case. All right? So the proposition for all x, letting adx. So basically, we are just using the Lie bracket over here, a definition of the adjoint map from there. We can define this adjoint map as before, by add x, y equals x comma y. Then e to the x, y, e to the minus x equals e to the add y. Okay, what does this mean? Oh, by the way, this is just another way of writing this. If you have y over here and y over here, that's just the same thing as this. But here, add e to the add x, y means this is exponential. So y plus add x, y plus add x squared over 2 factorial. It's like a exponential series. Da, da, da. Or if you want to use bracket, it's like x, y, x, x, y, 1 over 2, etc. So this is a consequence of the theorem that in the previous slide. But this is also possible to prove this directly, and that will be one of the homework problems for the next week. Okay, is everything okay? All right. So the next part is the complexification of a real Lie algebra. So when we have a matrix Lie group, we can make a corresponding Lie algebra, but that's only a real Lie algebra, not necessarily a complex Lie algebra. But usually it's easier if we have complex Lie algebra. So we want to make a real Lie algebra into a complex one. So let's say V is a finite dimensional real vector space, and the complexification of V is denoted V sub C. It's a set of all objects like this. Here, we think of this as this is a formal sum. Okay. Formal sum. Formal sum means this should be regarded as something like this. This is something like just a pair. It's a pair, but instead of writing this as a pair, we will just write like a sum. But it's a formal sum, so it should be considered like that. I guess it's a bit confusing. So, as a vector space, in other words, as vector spaces is really V direct sum V, because we have two components like V1, V2. Yeah. So if you really want to be very, very formal, you can just write, you can just use this pair instead of this. But we prefer this. We want to think of this as like a real, like a complex stuff. But anyway, as a definition, it should be a formal sum. And we can define. So obviously, this is a real vector space. This is a real vector space. So it's going to be a real vector space. But we want to give a complex structure. We want to make it into a complex vector space. So we have to define this. We have to define the way how we multiply I to an element there. So V1, I, V2. This is going to be minus V2 plus I, V1. This is the definition. Just like, yeah, it's a natural definition like that. if you want to use this, so because you are kind of comfortable with complex numbers, this seems quite natural. But if you are using, if you use like just this, v1 comma v2, it looks something like minus v2 v1. This is okay. They're the same, but we want to write something like that. But they should be considered to be the same thing. You know, this one's easier to remember than this, right? And of course, C times V1 plus I V2 is C V1 plus I C V2 for all C in real number. So now this is going to be a complex vector space. Then is a complex vector space. And V is a real subspace of VC. But technically, V is not a subset of this, but we can kind of embed. So via the embedding, how do you want to embed V? Just V plus I0. And V is going to be a subspace and a real subspace. Okay, we define the complexification of a vector space, a real vector space, but our goal is what? Complexification of a real Lie algebra, not just a vector space. So we want to, but real Lie algebra is a vector space, so we at least extended this to a complex vector space. Now, what's the next step? We want to give a Lie bracket structure there to make it really complex Lie algebra. The proposition is that there's a unique way of doing that in a natural sense. Finite dimensional real Lie algebra, and G of G sub C is the complexification of G. Here, of course, this is as a vector space. Vector space. We don't know yet how to make the complexification of a Lie algebra. So as a vector space, we know that. Then there exists a unique bracket. But just to distinguish this, let me write C on GC such that first GC with this bracket is a complex Lie algebra, and second, it is consistent with the original Lie bracket, meaning x comma y of this must agree with the Lie bracket for G, for all x, y in G. So we want to keep this. We want this to be consistent with the old one, but of course we have to extend in some way. But there is a unique way to do that. So so after giving this Lie bracket, now this is called the complexification of the real Lie algebra G. So there's no problem. We have a Lie algebra, real Lie algebra. You can just make it a complex one. It's a unique way in this sense. Okay, so proof, see the textbook. Okay, then how can we really understand this complexification? There is a very nice way to understand the complexification due to the following theorem. So we know that this is unique, and proposition G is, suppose that G is a Lie algebra inside this set of complex matrices. Suppose that this is a real Lie algebra such that for all non-zero x in G, Ix is not in G. Suppose that G is a real Lie algebra with this additional condition. And then, in this case, the complexification is simple. It's just set of all matrices of this form. Okay, x, y. Okay, let just for make it clear. This is the usual sum, so it's going to be in matrix such that x, y in G. So if you use this proposition, we can kind of compute, or we can understand the complexification of the examples that we usually see, these common examples. So for example, G, L, and R, C, this complexification is isomorphic to G, L, and C. And U, N of C isomorphic to GL and C, and etc. and etc. There are a list of stuff like that. Notice that they are equal. But let's see a proof just to understand what this means. So let's prove this thing. So what is U of n? This is the Lie algebra of the unitary group, and I don't think I've written this down, but this is a set of all matrices such that x star is equal to minus x. That's it. Now we want to find the complexification of this. But in order to use this proposition, we have to have this condition. If this is not true, then we cannot use this proposition, obviously. So suppose that x is in, let x is in small u of n, i.e., then this is going to be minus x. Let's see if what happens if you consider Ix. So what is this? So this is, if you have I, we have minus of this, right? And this, because of this, is x, which is not equal to minus Ix. That means Ix is not in U. So this condition is true. Okay, so we can use the proposition now. So this condition. So by the proposition, U and C is the set of all matrices x plus iy, where x, y both in U of n. But in fact, this is, if you collect them all, then it's just the whole set of all matrices. Because, of course, this is true. We only want to know this. So because if for all x in the set of matrices, if we say we can write this as like x1 plus I x2, where x1 is x minus x star over 2 x2 equals x plus x star over 2i. If we define x1, x2 in this way, then x1 star is minus x1, x2 star is minus x2. So then x1, both x2 are in U of n. So that means x must be in UC of UN sub C. So they are the same. So in this way, you can prove other things. So. All right. Now it's 3.7, the exponential map. And I'm going to do this at the same time. 3.8, consequences. Yeah, we already know the exponential map, but we define again matrix Lie group as before with Lie algebra G. The exponential map for G is the map. It's just the exponential map, only restricted to this Lie algebra to G. So it's really the same, only we just restrict the domain and the range. It's clear that whenever we have x here, its image is going to be in G, right? That's the definition, part of the definition of this. For every x, for e to the tx must be there for every t real. So this is good. Domain range are well set. In general, exp is neither one-to-one nor onto. However, still good. It is good enough locally. Locally one-to-one and onto. Locally bijective. So if you look at them locally, then this really tells us something. Okay. This is what this theorem is saying. I'm going to just write down the theorem, and then let me explain. This, we have some kind of condition, kind of a technical condition, but just think of this as we just restrict our domain very small to be very small, so that it's going to be one-to-one and onto. For this, let U of epsilon is the set of matrices where the norm of x is smaller than epsilon. And let's say V epsilon is the image of exponential map on this. Okay? And say G is a matrix Lie group inside this general linear group, and G, this is Lie algebra of G. then there exists some small number, some real number epsilon in this range, such that for all a in V epsilon, a is in G if and only if log a is in G. This is the theorem. Yeah, the proof is rather long, so I'll skip it. But if you are interested, you can always read the textbook. Okay, from just this by looking at this theorem, is may not not completely clear why it means one-to-one and onto. But if you think about this a little bit, then it does mean that this exponential map is locally one-to-one and onto. Let me explain in this way. I think I need to go to the next page. So we can always come back. So, all right. So let's see why that theorem means it's locally one-to-one and onto. Since 0 epsilon log 2, so epsilon is smaller than log 2, we have, this is a theorem that we stated earlier this semester. So this is 0 and this is u epsilon. Then this image is exponential map, go epsilon, and it will send 0 to the identity, right? This means that we have log map and then it's an inverse of each other. So if we take this epsilon very small, then this is really one-to-one. It's one-to-one. Exponential and log, they are inverses of each other. That's why we need this condition. Okay, so we want to know whether this is locally one-to-one and onto. So basically this means exponential of g. So locally, so g is somewhat like g. Let's say g is something like this. G is kind of a space like that, and maybe g, I don't know. Let's just write something like that, because they'll be eventually one-to-one and onto. But anyway, so we want to know that this intersect u epsilon equals g intersect. If this is true, then it's going to be locally one-to-one and onto. Why? One-to-one is already satisfied because they are inside this thing, right? So because exp, this is one-to-one and onto. So this is one-to-one and onto means this is one-to-one and onto. We have this condition. Okay, but we know that this is always inside this. You know, if g exponential is a map from this Gothic G to capital G, and exponential sends this to this, so this part is obvious. So basically, we want to know whether the other direction is true. Right? We want to know whether this is true. But what is that? This means for all a in over here, say just here, a is in G if and only if there exists x here such that e to the x equals a. That's what this is saying. Okay? This is inside this. This means for every a close to this identity, this is in the group, if and only if we have something. It's an image of this exponential. But this, because now the range is in the V, so it's like x equals log of a, right? So this means like log A is in G. And if you go back, that's what this theorem is saying. So A is in G, capital G, if and only if log A is in Gothic G. So that's this. So basically, that's the same thing as saying that exponential is locally 1 to 1 and 1 to 2. So this theorem has many interesting consequences. We will see some of them. So first, there exists a neighborhood. This means neighborhood. U of 0 in G and a neighborhood V of I in G such that exponential from U to V is a homeomorphism. So they are homeomorphic. This is simple. All we need to do is to take this to be U, this to be V, then we will get that. So that one is okay. Good. Another corollary. So suppose dimension of G, let me rewrite, equals K, the real dimension. Then this G is a smooth embedded submanifold of M and C of dimension K. So therefore, G is a Lie group. So smooth manifold with group structure. So it's a manifold. So manifold means if you look at locally, it looks like an Rn. So locally, so this means G is locally path connected because it's locally just Rn. So if something on some space is locally connected, then G is connected if and only if G is path connected. We used this before, or we defined connectedness using the path connected, but it is really the same as the connectedness. So it's okay to define the connected Lie group using path connectivity. Okay, there's a very interesting thing now. I think this is probably the thing that you want to remember, even though you don't use it. It's a really nice thing. Matrix Lie group with Lie algebra G. Then X is in G if and only if there exists smooth curve gamma of t in smooth curve in G such that the gamma 0 equals identity and d gamma dt evaluated t equals 0 equals x. The meaning of this is what's important. This means G is the tangent space of G at the identity. So if we have the G is a manifold, right? We know that this G is matrix Lie group is a Lie group and it's a manifold. So we have an identity group as a group element. We have an identity. So look at any smooth curve like that, okay, let's say smooth curve like that, then you can compute the tangent line over at the identity. Then this is going to be inside G. So basically what this theorem says that the tangent space at the identity is going to be G. So this is very nice. We have a vector matrix Lie group or Lie group. Its corresponding Lie algebra is just the tangent space at the identity. Oh, it's already 1 minute over. Okay, I will stop here. See you next